We're able to see different objects around us because of light. During the daytime, we are able to see all the different kinds of things. We see the road, vehicles running on it, trees, and we see these things because of the light from the sun. During nighttime, we are able to see the same things, but this time because of the glowing street lights. In the first case, the light is given to us by the sun, and in the second case, light is provided by the street lights. Objects which can generate their own light are called luminous objects, whereas the objects which cannot generate their own light are called non-luminous objects. Sun, stars, light bulbs are some of the examples of luminous objects. While the cement road, the steel pole, the trees and the benches are non-luminous objects. The human body is also non-luminous. We cannot generate our own light. Most of the objects that we come across in our day-to-day life are non-luminous. The book, the pen, wood, and so on are non-luminous. So how are we able to see the non-luminous objects? Yes, you will say that we see them because of light. Yes, that's correct. But the more precise answer is we see non-luminous objects because of the reflection of light. The light bounces off their surfaces. The reflected light, when reaches our eyes, enables us to see them. Now, where is this light coming from? Well, it's coming from the luminous source, the sun in this case. So we can say that the non-luminous objects reflect the light of luminous objects, and this reflected light is what helps us to see them. The light after reflection is traveling in a certain direction. And this direction is not just any random direction. Yes, if the incident light is in this direction, then the reflected light will always be in this direction. And this concept is nothing but the first law of reflection. Yes, light obeys some laws of reflection. We will understand those laws in our next video as they require some detailed explanation. But for now, we will discuss one important characteristic of light, and that is light always travels in a straight line. This observation was first postulated by Euclid in around 280 BC. You can also try to demonstrate the same thing at your home. Take two pipes, one which is straight with no bends and the other which is bent in the middle. Now look at the flame of the candle through an open end of the straight pipe. You will see the flame clearly, which is not so surprising. Now see it using the pipe which is bent. You wouldn't be able to see anything clearly. Use different pipes that are bent in different ways and try to look at the flame through each of them. Again, you wouldn't be able to see the flame through any of them. What does this imply? Well, from this we can imply that light takes a path of a straight line. Otherwise, we would have been able to see some or all of the light through any of the bent pipes. This fact is, however, not quite entirely true. Einstein predicted that light can be bent by gravity. And it has been observed that during total solar eclipse, when the moon is between the Earth and the sun, the light from the stars present behind the sun is visible to us. Well, it shouldn't be if light travels in a straight line because it should be blocked by the sun. But this happens because of the light coming from the stars is bent by the gravitational field of the sun. Light is also bent by the gravitational field of the Earth. However, the sun being 1,000 times bigger than the Earth has a more massive gravitational field around it, and hence it bends the light by a comparatively greater degree. The Earth's gravity deflects the light by about 1/1,000,000th of a degree. That is really small. Hence, for our purpose, it's perfectly fine if we think of light traveling in a straight line. Because of this, we can think of light as straight line paths with arrowheads traveling in different directions. A light source emits light in all possible directions. For example, this fluorescent glowing bulb is emitting light in all the possible directions. All these lines with arrowheads are called light rays. You can think of a light ray as an infinitely narrow beam of light. In reality, a ray of light is something which is not visible. This is just a way of explaining how light travels. A straight line with an arrow in the direction of propagation. It is easy to draw a ray of light on a piece of paper, and this depiction of light is very useful. Understanding light as rays in different directions, we can study the properties of images formed by mirrors. We will see them in our future videos. We will start with the reflection of light in the next video. This light bulb glowing. It's emitting light in various directions. In our previous video, I told you that the light can be thought of a straight line with arrowheads representing the direction of propagation. This is a light ray. And just like this one, there are infinite rays of light from this bulb that can be drawn, each traveling in a different direction. Previously, I'd also mentioned that this is just a way of explaining how light travels. We cannot really see a ray of light. However, we can think of it as infinitely narrow beam of light. Yes, it's infinitely thin. This representation of light helps us draw ray diagrams, which in turn helps us to identify the position of the image of any object. We will see those in our future videos. So from now on, whenever I mention the word light, it should be assumed to be a ray of light and not a beam of light unless mentioned otherwise. Now light obeys certain laws of reflection. Since light can be thought of as a ray, we can say that a ray of light obeys certain laws of reflection. And since there is reflection here, I need to first bounce off this light, or in other words, reflect this light off some surface. Which surface should I use to reflect the light? We've seen that a shiny mirror surface reflects most of the light. Hence, we will use the surface of a plane mirror to study these laws. Consider this plane surface of the mirror then. Suppose one of the rays of light from the bulb strikes the mirror at this point. This is called an incident ray. We know that this mirror will reflect this ray, and the reflected ray will travel in this direction. Why only in this direction? Well, it's because of the first law of reflection of light. To understand it, let's draw a perpendicular to the surface at the point of incidence. This line is also called the normal. Here are the two laws of reflection that any light ray obeys after reflection. Pause the video and read both the laws. To understand the first one, we need to know what angle of incidence and angle of reflection mean. The angle of incidence is the angle made by the incident ray with the normal. It's denoted by the letter I. And you can easily guess what the angle of reflection is. It is the angle made by the reflected ray with the normal. And it's denoted by the letter R. So our first law says that the angle of incidence is always equal to the angle of reflection. I is equal to R. Here I is equal to R if the incident ray strikes at this point, then the reflected ray will travel along this direction only. And this is to keep the measure of R same as that of I. If I move the incident ray here, then the reflected ray will also move to keep the measure of R same as I. So I will always be equal to R. Okay, so this was about the first statement. What about the second statement? The second one tells us that the incident ray, reflected ray and the normal all lie in the same plane. So if I draw this scenario on a piece of paper, I will get this. This incident ray, the reflected ray and the normal, all three lie in the plane of the paper. The second law tells us that they will always be on the same plane. For example, if the reflected ray is in this direction instead of this, then the diagram will look a bit like this. The incident ray and the normal are in the plane of the paper, whereas the reflected ray is not in this plane. This violates our second law, and hence this ray will not be reflected in that direction. This is just not possible. It only has to be this way. I will be equal to R and they will lie on the same plane. Every light ray obeys these two laws. Yes, no matter which direction the light ray is incident in, the reflected ray will travel in such a direction such that laws of reflection are satisfied. Okay, here's a question for you now. If a light ray is incident perpendicular to the surface of the mirror, then in which direction will the reflected ray travel? What will be the angle of reflection in this case? Pause the video and give it a thought. We know that the angle of incidence is the angle made by the incident ray with the normal. And the normal is the perpendicular line to the surface at the point of incidence. But since the incident ray is also perpendicular to the surface at this point, both of them coincide. Hence, the angle of incidence I is equal to 0 degrees. We know that every light ray satisfies the law of reflection. Therefore, the angle of reflection R will also measure 0 degrees. That means the reflected ray will travel in this direction opposite to the incident ray. Yes, it will overlap the incident ray as well as normal. This reflection of light ray looks quite nice, isn't it? We don't really have to draw a normal or measure any angles here. The perpendicular reflection or the 90-degree reflection of a light ray is quite useful. Useful where? In determining the position of images of objects reflected from curved mirrors. Curved mirrors? We will see what we mean by that in our future videos. Okay, so this lesson was about the 2 amazing laws of reflection. You can also verify these laws by performing a simple experiment. I will show you how in the next video.